Okay. Okay. Let's get started. So, one moment. 等一下，遥控器。Okay. So last week we talked about the gradient descent, and we talked about we use a polynomial regression to talk about the concept of regularization. Okay. So before we start today's lecture, okay. The one first thing I want to remind you guys is that we don't have lecture next week, okay, because I'm out of the country for student recruitment. So so the next week lecture is canceled, but it will be made up like at the end of the semester. And one more thing is that 2 days ago when I attended the International Student Office meeting for this student recruitment, okay, I was told that okay, because by the time I came back, which is next Saturday, the second coming Saturday, okay. So I still need to do like the quarantine, right? 3+4 quarantine, okay? And the school actually originally, okay, that the +4 3+4, that 4 days, I'm supposed to be able to teach classes. Previously, according to school regulation, but our school just changed that, okay, they say like okay, that 3+4, okay, the whole period including that 4 days, okay, I will not be able to come to the class in person to teach classes, okay. So as the result, okay, so first, as I told you, the lecture next week will be canceled, but the lecture in the next week, okay, will be held online, okay, according to school regulation, because actually 3+4, because I came back on Saturday, so Sunday, Monday, Tuesday, because our class is Thursday, so I originally I didn't think I have any problem coming to the lecture, but now the school has changed their like the regulation, so I have to teach the lecture in the second coming Wednesday by online class, okay. So this change is like it's made to comply with school regulation. It's not like I prefer online classes, okay. I actually prefer to come to lecture to talk to you face to face, okay. So yeah, just want to remind you that, okay. And also, okay, remember, okay, I announced the first project last week, right? So whoever that hasn't checked the e-class for the project, please do so as soon as possible. And if you have not found your teammate, okay, remember I mean for the small projects, you need to find teammate to form a group, okay, of 2, okay, and I think the deadline is end of this week. Is that right? When is the deadline that I announced? Eh, 助教在吗？你们记得那时候讲是 end of this week, right? This Saturday midnight, right? 是下礼拜还是这礼拜 ？Okay, sorry. So it will be next Friday. Okay, next Friday. So let me put it this way. Okay, before our next lecture, okay, which is online, of course. But before the next lecture, I expect you guys to form a team of 2, okay, for the project, okay, and if you haven't done that, before the deadline, the TA is going to randomly assign a teammate for you, okay. I don't want that to happen, okay. So I just want to remind you about this once again, okay. So come back to our discussion on regularization. Okay, we talk about ridge regularization, which is also known as L2 regularization. Okay, the other one, which is actually well, I wouldn't say it's more famous, but I would say it's as famous as the ridge, is a lasso regression. Okay, lasso regularization. I think I should. Sorry. Okay. The lasso. Okay. So compared with the lasso, you can see that the difference is that, okay, in lasso we pretty much add a square of all the coefficients, the sum of the square of all the coefficients as the penalty term in the cost function. That's the ridge. But for the lasso, okay, we use the absolute sum of the absolute value of all the coefficients. Okay, add this term as like we add this term to the cost function as a penalty, okay? And similarly, okay, when you minimize, because our gradient descent, okay, will help us to minimize the cost function, right? So when you minimize the cost function here, okay, it's going to minimize these coefficients as well. Okay, so obviously it's also going to put a constraint on those coefficients. Okay, that is how lasso regression. Okay, sorry, lasso. Okay, regularization. Okay, concept. Okay, take place. Okay, so basically, you will see something similar to ridge regression. Okay, so for example, if it's a linear situation, and by the way, here this alpha obviously is a term that you can use to control how much emphasis you want to put on this regularization. You want to put on the constraint of the coefficient. Okay, the higher the alpha value, the more constraint you put to this coefficient. So you can see that, okay, as alpha value grow from 0 just means there's no regularization at all. Okay, and in that case, this blue line obviously finds the trend of all these points. Okay, this is obviously a linear model. Okay, we are talking about linear regression, but as the alpha value increase from 0 to 0.1 to 1, you can see that, okay, the coefficient, okay, here, I mean, when I say coefficient, okay, the theta 0, the bias is not included. So that is, you can see, the theta 0 is not included. The bias is not included. So that's why, okay, I mean, you will still see the bias, the bias is not going to become 0, no. But the other one, such as, the coefficient for the x, which obviously represent the slope, right? The slope become, smaller and smaller. And when alpha become 1, it's going to be, very close to like a flat line, okay, which means your theta value, your theta 1 value is, getting close to 0 actually, okay. So this is just to show you how much powerful this lasso regularization is. Okay, same thing can be said for the polynomial regression. So this blue line indicates like when the polynomial regression when alpha is 0, meaning there's no regularization at all. And when alpha is just 10 to the power of -7, just a very tiny value, you can see the curve becomes much smoother, okay, much smoother. And when you set alpha to be 1, okay, it's a strong regularization, so the result is almost close to a flat line, okay. So so just by observation, one thing you can you may observe is that lasso regularization is perhaps stronger than the ridge, okay, because you can see for ridge, even when alpha is 10 to the -5, okay, it's still like a kind of like a curve, much, it's much curvy than what you get, okay, with even smaller alpha value, okay. And when alpha become 1 in lasso, it's almost a flat line. But here, when alpha is 1, the ridge, well, it is also like a much flatter, but not as flat as what you got by using lasso. Okay, but obviously, all these are controlled by alpha value, right? We have alpha value for ridge, we have alpha value for lasso. So depending on how much you put for this coefficient, as I said, the higher alpha value is, the more regularization you put to, more constraint you put to those coefficient anyway. So the importance here I want to emphasize is really not that, okay, lasso has more constraint than ridge. No. The concept here is that, okay, they actually, I already talked about this already. So the differences between ridge and the lasso is not about the power of regularization. It's about, you may think they both put the constraint, and one use the sum of squares. One use the sum of absolute value. It looks like at least conceptually they don't look much different, right? They both put the constraint, right? But so what's the difference? There's a very important difference. Okay, let me show you with this figure. Okay, so this figure, okay. Oh, by the way, I also have to tell you, okay, one important terminology. Okay, lasso is also called L1. Ridge is L2. Okay, I think this is very easy to remember because ridge is the sum of square terms, right? And lasso is the sum of absolute value, which is power of 1, obviously. Okay, so one is L1, one is L2. Okay, but here, okay, these figures actually show you the differences between lasso and the ridge. Okay, so the top Okay, what should I say? First, I want to tell you that, okay, the x-axis and the y-axis represent two different parameters or two different features. Okay, so you have x1, x2. Okay, so for x1, x2, I mean, well, you have like x1 you have theta 1, right? x2 you have theta 2, right? Also, so the x coordinate represent the theta 1. Y coordinate represent the theta 2. Okay. So, so what's first? I mean, let me explain the difference between the upper row and the low. I mean, the lower row. Okay. These two figures were obtained by using reach. These two figures were obtained by using lasso. Okay, this is the first thing I want you to know. Okay, these two are obtained by L1. These two were obtained by L2. Okay, so second thing is, so what's the difference between these two columns? Okay, this one show you, okay, when you use well, this column show you when you use regularization technique, okay, to do like training, what happens to the cost function? To the cost function. Remember, in cost function there are this term and this term, right? One is, you know, maybe in our particular example here, this is MSE. Okay, I mean, of course, depending on your problem, okay, you may have different cost function, okay, but here let's assume we use MSE. I mean, for our example here we use MSE. I mean, there are other cost function obviously, okay, and this is the penalty term for the regularization. Okay, obviously L1, L2 will have different penalty term here, right? Okay, so when I say the trend of the cost function, I mean the trend of the whole thing. Okay, the sum of these two terms. Okay, so here, this shows the sum of the whole cost function. Okay, so you can see that, okay, they actually traverse, okay, you know, what should I say, like the path, I mean, looks like a little bit, you know, at least for I should say this is L1. Okay, it goes like I mean, we know like the optimal location is here. So starting from a random place, it goes toward this optimal location, and gradually converge to here. But there's some fluctuations, you know, when it converges to the optimal. Okay, and this is lasso L1. For reach, it is much smoother. It goes almost straight. It goes almost straight to the optimal, right? Okay, but okay, this is for the cost function. But what I want you to observe is the penalty term. Okay, the penalty term. Okay, this is very interesting. Okay, because for the penalty term for L1 for lasso, it's going to be absolute value of theta 1 plus absolute value of theta 2, right? Okay, so it actually, you know, get the theta 1 and the theta 2 when you trend it Okay, this is because parallel return. I mean when you have more and more constraint, eventually, theta 1 and theta 2 is going to getting closer and closer to 0. Okay, supposedly getting closer and closer to 0. But for L1, okay, it will reduce both theta 1 and the theta 2, okay, at the same rate. At the same rate. So you can see this reduction from here to here, it's pretty much, you have pretty much the same reduction rate for theta 1 and the theta 2, right? But when the theta 2, okay, obviously, when you start, when the starting location is here, the theta 2 is value is smaller than the theta 1 value, right? Okay, because this is this represent the origin, right? So if you just if you just assume each of these as a 1 unit, then 1, 2, 3, 4. So the randomized initialization location for theta 1 is 4. For theta 2 is 1, 4, 1, right? 4, 1. So after a while, you can see because they reduce at the same rate. So theta 1 will become 3, and theta 2 will be reduced to 0, right? But when theta 2 is reduced to 0, okay, well, you cannot further reduce theta 2 because that's a minimum. That's what the minimum you can get for the square for the absolute value of theta 2, right? Okay, so the theta 2, will basically, remain 0. Remains 0. But theta 1, of course, will continuously be reduced, okay, until eventually they will reach the origin, okay. So this is like what happens when you use L1 regularization, okay. And on the other hand, okay, if you use ridge, the L2, okay, at the same randomized initialization location, okay, what we want to reduce is theta 1 square plus theta 2 square, right? Okay, so if you are here, theta 1 is 4, theta 2 is 1, right? I just told you, right? Theta 1 is 4, theta 2 is 1. So 4 square plus 1 square. So you have 17 square, 17, right? So you are trying to reduce this term. But when you try to reduce this term, it means you are reducing this term, right? So originally it's 17, right? Okay. So as this value gets lower and lower, what you are going to get is going to be, this obviously represents a circle, right? This represents a circle, formula, right? So when you have smaller and smaller sum of squares, what you are going to get is that, okay, you are going to go straight to the center of the circle. Okay, so yeah, theta 1 and theta 2 also gets reduced. Okay, but in L2 or in ridge, okay, whatever you call it, okay, you can see the reduction rate of theta 1 and theta 2 are different. Okay, actually theta 1 gets reduced faster than theta 2, right? And eventually, of course, they both converge to 0, right? So why do I want to emphasize this to you? Okay, so what is the, the point, okay, to talk about this, different convergence rate of different, coefficient. Okay, let me put it this way. Okay, eventually, okay, when you use this regularization concept to constrain your model, okay, as I say, if right now we are using this for like a linear regression or polynomial regression. Really, we are only talking about very few coefficients, not a lot of coefficients. But in the future, when we use a deep learning model, we are going to have many parameters, many coefficients. Okay, and some models may have so many parameters such that the model becomes very heavy. When I say the model becomes very heavy, I mean like it will require a lot of computation. Okay, for example, you need a faster GPU card to run your model. Okay, a faster GPU card, or like when you try to put your model on, for example, an embedded system. Okay, because embedded systems such as like there are so many different embedded systems that for example, your phone is the most common embedded system that you carry every day, right? So, or like when you drive a car, the car, of course, even though it looks big, but it is also an embedded system. Okay, in most of those embedded systems, it has only limited computation power. Okay, so you want your model to be, what should I say, lightweight, so that your embedded system is able to execute your model. Okay, I'm not talking about linear regression. I'm not talking about polynomial regression, because as I said, these models, they are machine learning models. Majority of machine learning models are lightweight. I cannot recall any machine learning model that is heavyweight. Okay, but deep learning models are different. Okay, there are so many deep learning models. They are, very heavy. Okay, so sometimes we want to make some model lightweight. Okay, so in this if you want to achieve this goal, okay, you can also use lasso. You can also use L1. Why? Because you can see that, okay, lasso will first force the coefficient, smaller coefficient. It will force the smaller coefficient to 0 first, right? Lasso, for example, here, okay, remember, you can see theta 1 is 4, theta 2 is 1, right? So during the training, it will actually enforce the L2, because L2 is smaller. Theta 2 is smaller. So theta 2 becomes 0, right? Theta 2 becomes 0 first, right? So in your model, if you are able to reduce some smaller coefficient to 0 first, then your model will not need to compute so many coefficients or so many parameters, whatever you call it. So it also means your model becomes much more lightweight. Okay? But on the other hand, if you use L2, it will reduce all the terms to all the coefficients to smaller terms. But it will not eliminate any of them. It will not eliminate any of them. Okay, so L2, if you want to use L2 to reduce the size of the model, it's not likely. okay? Because you pretty much cannot get rid of any parameters, okay, by using L2. So this is a big difference, okay? I just want to emphasize this to you, okay? So other than the regularization, okay, power of regularization, okay, that Ridge and the Lasso bring to you, okay? If you want to make your model lightweight, okay, L1 or Lasso is also a technique you could try to use, okay? So, well, I already explained this, okay? So, yeah, I mean, for lasso regularization, because you use like the sum of absolute values, so, you add this term, okay, penalty term to the cost function, and obviously this penalty term is non-differentiable when any of those theta I becomes 0, right? Because it's going to be like I mean, when you differentiate it, I mean, absolute value is like this, right? It goes down, okay, until when it reaches 0, okay, when the value is negative, it becomes positive. So it's well, everybody knows the absolute value, y equal to, you have this figure, right? So this point is non-differentiable, right? Okay, I'm not talking about advanced calculus. This is obvious, right? Because like if you look at from the right hand side, the slope is 1. If you look from the left hand side, the slope is -1. Okay, so there's a discontinuity, okay, for the slope, okay, at the value x is 0. Okay, so or the theta I is 0. Okay, so but we have in the gradient descent, we are still be able to to deal with the discontinued points. Okay, so but I don't think you need to worry about this detail. Okay, so don't worry about this. You just need to know that, okay, even if you use lasso, which may have a discontinued, may not be differentiable at some point, okay, the gradient descent also work for you. Okay, so this is the example of the code, okay, using lasso class. Okay, so it's a very simple. You just specify, okay, lasso regression, okay, and you specify the alpha value, okay, and that's it. Okay, but here this one is used, I mean, along with the I believe it's like for linear regression. Okay, so eventually, I mean, we are going to talk about L1 and L2 in that can be used in the deep learning. Okay, so don't worry about this. I mean, So the third one is elastic net. Okay, elastic net is pretty much like you can treat it as a combination of ridge and lasso. Okay, so you can see it add these two terms into the cost function. So the important thing is, we introduce additional gamma value here. Okay, so we multiply. This is the term for the lasso, right? We multiply this penalty term for lasso by gamma, and we multiply the penalty term for ridge, okay, by 1 minus gamma divided by 2. Okay, well, but this divided by 2, okay, actually is originated from the lasso, right? In the lasso we already have this divided by 2. Okay, lasso. Oh, sorry, ridge. We have this 1 divided by 2 in the ridge originally anyway. So actually what we got extra here in the elastic net is this 1 minus gamma. Okay, so we have gamma here. We have 1 minus gamma here. So pretty much like when gamma is 0, the elastic net becomes L2. When gamma is 1, okay, this term becomes 0. Okay, so the elastic term becomes L1. Okay, so depending on the value of gamma, okay, the elastic net behaves like somewhere in between L1 and L2. Okay, so but you probably don't need to worry about this. Okay, because eventually, like in the deep learning, we don't use elastic net a lot. Okay, so this is an example of using elastic net with the linear regressions. But I just want to tell you like a regularization concept in the through this linear and polynomial regression. Okay, so last concept to cover, okay, in this set of slides is early stopping. Okay, remember, okay, the purpose to introduce regularization is to fight with overfitting, right? Okay, because when the model is overfitting, it doesn't generalize so well with the new data. Okay, so okay, there's another way you could use to fight with with overfitting, and the cost is actually very, very minor. Actually, it actually saves the time for training. It's called early stopping. Okay, let's look at this. Okay, so remember I told you, okay, the learning curve. There are a couple of ways to represent learning curve. Previously, I used like the x axis for that learning curve that I talked about. Okay, is the size of the training data. Remember? Okay, but if you remember, I told you at that time. Okay, another way to represent the learning curve is to use the number of epochs or number of iterations for the training. Okay, I mean these two are roughly equivalent because the more iteration normally means the more data you considered in the training anyway. Okay, so this represents the number of iterations. Okay, and the y-axis, as I said, okay, for the learning curve, I mean you could use either the error or accuracy, right? Okay. And here, I mean, we use RMSE, which is also one type of error, right? So normally, I mean, as I said, for the training set, you are going to get slightly lower. You are going to get lower error. Okay, which is so the RMSE for the training set is represented by red dotted line. Okay. And for the validation set error, okay, is represented by blue line. Okay, and remember I told you, okay, when these two lines are getting, more and more far away, that's the case when the overfitting happens. Remember? Okay, I talked about this like last week. So to be honest, okay, because you use training set for training, so it is, the training set. I mean, as more and more, as you use like more and more iterations to train your model, okay, you will see, this the error for the training set gets actually reduced more and more. But at the end, I mean, it may be almost like flat, but still like it's going to be, in the worst case, it's going to be flat anyway, okay? But for the validation set, okay, and initially it goes down, but at some point of time, it may become flat. I mean, for some point at some point of time, and then eventually it's actually going to go up. That is when your model starting to pick up those noise. Okay, and that's the indication that the model becomes overfitting. Okay, so obviously, look at this figure. When should you stop model training? Should be here, right? But the issue is, you don't know. You don't know how many iterations you should stop the model training in advance. You don't know. Okay, so the early stopping concept is very simple. Okay, it just try to it just record the validation error. Okay, so this it memorized. Okay, so in the early stopping approach, basically after the training of one iteration, you first save this model. Save it because it may be the best one. Okay, you first save this model and measure the validation error. If this validation error is lower than the previous one, you pretty much remove the previous copy of the model. Just save the current copy. Okay, and then you start working on the next iteration. So the next iteration, if it doesn't improve, okay, keep in mind this. At this point, it may be even though I draw this one as like a so smooth, but actually it may have some jitters, but it may be go up and down a little bit. So you may want to so you may see like in the next iteration, the validation error gets up or down a little bit. Okay, when it goes up, of course, you don't want to save this current model because, well, the performance of this model is worse than the previous iteration, right? But you need to remember, okay, this is, so you just keep working on, okay? So after, say, like after a number of iterations, say like 5 or 10, after 5 or 10 iterations, if you still cannot find a lower validation error, then you should stop your model training. Okay, you stop it, you cut it, you no longer train it. Further, and then you basically remember. You will save a copy of the best model that you have so far for the validation error, right? So you are going to recall. Basically like restore that model back and use that as your training result. This is called early stopping. So basically, for early stopping, you are going to, it's okay to set a very, very large number for the iteration, because eventually the training will be stopped, okay, before the model run into like overfitting anyway. Okay, so you don't need to worry about like setting a large number for iterations. Okay, so early stopping, how we of course like for linear regression or the implementation, this rollback is just like we just try to get the best, the model with the best performance back, just copy that back. That's called rollback. Okay, so don't worry about this. So this is like the implementation of early stopping on the linear regression and the polynomial regression. Okay, this is just an example for that. Okay, I believe this is for the linear regression, but for the deep learning, we have a different implementation for the early stopping. I just want to tell you the concept of early stopping, which will become very useful. I mean, in the deep learning field. Okay. Remember, like we have slang say like there's no free lunch, right? There's no free lunch. Okay, but the early stopping is a technique that you do get free lunch. Okay, because it actually tells you to stop training early, and you get better performance, right? So it's like you get better performance without sacrifice, without costing you a lot of overhead. Okay, so this is a very good technique, and this early stopping concept has been used in deep learning model training very often. Okay, so that is it for the getting started set of slides. So I will. Any question? I think it's about time for the break. So let's take 10 minutes break. When we come back, we will start the next set of slides. Where is it? Here. Okay.